Dr. Chen here. So we're going to study gravitational force in this lecture video. And Newton's law of gravitation says if we have two particles, and as long as they have mass, there is going to be an attractive force between those two particles and pointing toward each other. So in the direction that you joined these two particles as none, and the force is along the direction, pointing each other. And from Newton's third law, we also know it doesn't matter what's the difference of force, the mass of those two particles, the force from 1 on 2 and the force from 2 on 1 would always equal each other, have the same magnitude. Of course, the direction is opposite. This is Newton's law of gravity. It says the gravitational force between two mass is given by a constant. We call it capital G, gravitational constant, capital G, 6.67, 10 to the minus 11. Its unit should be Newton times meter square divided by kilogram square. So the right-hand side will give us a unit of Newton eventually. The gravitational force between two particles proportional to this gravitational constant G times the mass of object 1, mass of object 2 divided by the distance square of those two particles. Distance between those two particles and then square. Okay. Now suppose if we have M1 and M2, and we know the force is F. Now we do a calculation, the gravitational force. Let's say on everyday objects, if we have two balls, and the mass of those two balls are 0.5 kilogram each, and they are separated by a distance of 0.5 meter. What would be the gravitational force between those two objects? So we just need to plug in the gravitational constant, mass of ball 1, mass of ball 2, divide by the distance between those two balls, and then square. And we'll find is in the magnitude of 10 to the negative 10 Newton, which is a quite small number. And this is why in everyday life we basically only experience gravitational force from the Earth because mass of the Earth is largest object that is close to us. Now let's see, we have M1 and M2, the force is F. What's going to happen to the force if we make the mass of object 2 halved and keep everything else the same? Basically keep M1 the same, keep distance the same, which would be the correct answer after we decrease the mass of 2. Now, we have to go back to Newton's third law, right? So if we have a force from 1 on 2, we're going to have a reaction force from 2 on 1, and they have to equal magnitude, opposite direction, like shown here. Now, even if we have mass of 2, what's going to happen to the force between them? The force is going to be halved, right? Force is going to be halved, but not only force 1 on 2 would be half, force 2 on 1 also going to be half because they all follow the same equation. If we reduce M2, the force from 1 on 2 and the force from 2 on 1, both of them is going to be halved. So the correct answer is C. Then we will wonder why the acceleration of free fall is 9.8 on surface of Earth, which is something you already checked using your experiment, right? Why is that? And this is because the mass of the Earth and the radius of the Earth. The particular mass and the radius of the Earth give us 9.8. So we can do some quick calculation. So we know the weight on Earth should be mass of the object times a constant, which is 9.8. But we also know the weight should be coming from gravitational force, so it should be g, mass of the Earth, times the mass of the object, r squared. Now if we compare those two equations, we'll find out that g equals gravitational constant times mass of the Earth divided by radius of the Earth squared. So let's check whether it gives us 9.8 if we plug in the number for the mass of the Earth and the radius of the Earth. So let's see, g of Earth should be given by 6.67, 10 to the negative 11, and mass of the Earth 5.972, 10 to the 24 kilogram. Radius of the Earth 6.371, 10 to the 6 meter square. Unit should be meter per second square. You punch this into your calculator, and we find the answer is 9.81 meter per second square, and this is why the acceleration of free fall on the surface of Earth is 9.8, roughly 9.8. Now, on the other hand, if we move to the moon, what would be the acceleration due to free fall on the surface of the moon? We just need to do the same thing by plugging in the mass of the moon, which is 7.35, 10 to the 22, according to this problem. And the radius of the moon, say the moon is a little bit smaller than the Earth, square meter per second square. Everything in we find is 1.625 meter per second square. So the acceleration due to free fall on the moon is much smaller, which is understandable because the moon has much smaller mass, and the density of the moon is roughly the same as the Earth. And if we compare the acceleration due to free fall due to gravitational force, the free fall acceleration on the surface of the moon is roughly, and we can check roughly what we have on Earth, 9.8 divided by 6, roughly. Okay. And this is exactly why if you watch some video clips of astronauts on the moon, they are not walking, and they want to walk, but the g on the moon is so small, it appears to us they are running and hopping on the moon.